everyone! Welcome to part 3 of chapter 10. Last time we learned all about the different types of reactions. We learned that there are combination, decomposition, combustion, single displacement, and double displacement reactions. We learned how to recognize those different types of reactions and to predict the products and to balance the resulting equations. Today's lecture is going to focus solely on double displacement reactions. We are going to, look deeper at double displacement reactions and see how to write net ionic equations that are going to show the actual reaction that is happening in solution. So let's go ahead and get going. So you'll likely have noticed that in all of our labs, we typically start with aqueous solutions. Or if you haven't noticed that, you may have noticed that in the last lecture, our double displacement reactions were all aqueous when we started. The reason for that is that when we dissolve our reactants in solution, that turns them into ions. And those ions allow them to come in close contact to react. So for example, let's say these two reactants, potassium chloride and silver nitrate. If we were to put both of those solids together, and they're both white solids, if we were to put the solids together and kind of mix them around, no reaction would really happen. But if instead, all we've done here is instead of making these solids, we've now made them aqueous, which means I put my potassium chloride, that white powder, I put it into water and I stirred it up. And then I did the same thing with my silver nitrate powder. I put it into water and I stirred it up. And so now when I mix those two solutions, we do see a reaction. We will get a precipitate that forms, a silver chloride solid. So the difference here is that in this one, they were both solids, and here they were both aqueous. So by just dissolving these compounds in water, we allow those ions to collide with each other. And reactions are all about collisions. If our particles can't kind of come into contact with each other, then they can't react. Here, when we have potassium chloride solid and silver nitrate solid, those ions were all kind of bound up. They were already bonded and locked into that crystal structure. But when in this example, we dissolve them in water, that frees up those ions and they're floating around as, K plus and Cl minus or Ag plus and NO3 minus. And since we freed up those we freed up those ions, they can now float around in solution, bump into each other, and react to make our products. So the actual reaction that's happening is that this chloride ion is reacting with this silver ion, right? The chloride ion is reacting with the silver ion, and it's forming silver chloride. You'll notice that the potassium and the nitrate were aqueous in aqueous solutions at the beginning, right? Here's aqueous and aqueous. So potassium and the nitrate are both aqueous. And in here, it's still aqueous. So that means the potassium and the nitrate were actually not a part of this reaction at all. They essentially just kind of floated around in solution and watched the reaction happen. So today, we are going to look at what reaction is actually taking place in these double displacement reactions. So we're going to focus on the ions that are actually forming the solid, or the ions that are forming the gas, or the ions that are forming water. Okay, and this is going to give us our net ionic equation. So that's kind of the focus of today's lecture. So we have 3 different types of equations that we can write when we write these reactions. The first one is the molecular equation, and this is just our normal balanced chemical equation, the one we've been writing throughout the whole course, right? So if you hear me say molecular equation, that's just our normal balanced chemical equation. It's going to show all of our reactants intact, just like normal. You're not going to break them into ions, you're not going to do anything, you're just going to write the 2 things that are reacting and then show the 2 products, just like normal. One of the new types of reactions is the complete ionic equation, and that's actually what I just showed on the bottom of the last slide. It's going to show all of the soluble ionic substances dissociated into ions. So remember, by soluble, I mean anything that is aqueous. Okay? And then the net ionic equation is going to cancel out these spectator ions. And in the last example, our spectator ions were potassium and nitrate. Those are ions that appear on both sides of the equations as aqueous ions because they don't take part in our chemical reaction. And so we're just going to show the actual change that's taking place. So the focus of today's lecture is to learn how to write this net ionic equation from starting with this balanced molecular equation. So let's look at this a little more in detail. Our molecular equation is going to show all of our substances as either elements or compounds using the appropriate formulas. So just like normal, remember, molecular equations are our normal balanced chemical equation. It's super important that you are going to write the states of matter. You need to write solids with an S, gases with a G, liquids with an L, right? Remember, that's a cursive L there, or as dissolved in water with a Q. Very, 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 very important that you do this part correctly. If you do the phases of matter wrong in this step, you're going to get all of the rest of it wrong. So double check, triple check, make sure that those phases of matter are correct. Remember, we learned solubility rules last time. We said that anything that had an alkali metal, so sodium, potassium, lithium, rubidium, cesium, right? All of those, they will always be aqueous, all of those alkali metals. We also learned that things with ammonium, nitrate, and acetate are also aqueous. Any other substance, I want you to look it up on that solubility chart. It was in the slides last time, and it's also posted for you on Canvas. You're going to need to use that, like I said, if it doesn't contain one of those ions that I want you to memorize. So for this lead nitrate here, that's aqueous because anything with nitrate is always aqueous. Our potassium iodide is also aqueous because it has potassium, and potassium is an alkali metal. So potassium nitrate, definitely aqueous because both potassium and nitrate cause anything that they're bonded to always be aqueous. And then lead iodide. Lead iodide doesn't contain any of the ions that we have to memorize, so we would go look that up on our solubility table. If you look up lead iodide, you would see that there is an I. That means that it is insoluble. Therefore, we put an S to say it's going to form a solid in solution. Okay, so this is where we're starting. This is our molecular equation, and again, it's just really important that you show the states of matter and that those states of matter are correct. All right, so on to a new type of equation. Our total ionic equation is going to show all of the dissolved ionic substances as ions, which means you are going to split apart anything that's aqueous. If it's not aqueous, then you're going to show it using the molecular formula, just like normal. So we are only going to split up things that are aqueous. So here we have, the first one is lead nitrate, and that's aqueous. So that means we need to split this apart. So when we split this apart, we need to break it into our ions. Remember that lead is one of those that can have multiple charges. So when we're kind of thinking about this uncircling and switching, this 2 came from the lead, so that's telling us it's lead 2+. Okay, so when this splits into ions, it's going to split into lead 2+, and that's going to be aqueous. And then there are 2 nitrates, because that subscript here is telling us there are 2 nitrates. Okay, we were only uncircling and switching to figure out the charge of that lead. So that 2 here is telling us that lead was a 2+, but we need it to be a coefficient here to say, okay, there are 2 nitrates when this splits apart. Both of these will have aqueous because the compound was aqueous. All right, now we're going to split apart potassium iodide. So it's going to split into potassium and iodine, but this 2 out front is going to distribute to both of them. So we're going to get 2 potassiums and 2 iodines. Okay, now we're also going to split apart potassium nitrate because it's also aqueous. It also has a 2 in the front, so that's going to give us 2 potassiums and 2 nitrates. So 2 potassiums and 2 nitrates. Again, both of those substances are going to be aqueous because this was aqueous. That's why we're splitting it apart. You'll notice that lead iodide is the only thing that doesn't dissociate into its ions. The reason for this is that lead iodide is an insoluble substance. It's a solid, so we don't split apart solids. The only thing you are going to split apart are aqueous ionic compounds. All right, so now that we have the total ionic equation, so that's what this is. That's the one we made in the last one. Now we are going to cancel out our spectator ions. So spectator ions are ions that do not undergo a change. They're going to show up exactly the same on both sides of the equation. So like here we have 2 nitrates and we have 2 nitrates. So those are going to get canceled out because they are exactly the same on both sides of the equation. This is like in math class when you can cancel out an x because it shows up on both sides of the equation. Same thing here, like we have 2 potassiums and 2 potassiums. So those are going to get canceled out. So in this example, potassium and nitrate are considered spectator ions because they are watching this equation happen. Okay, they're watching the reaction happen. They're just floating around in solution. They're not forming anything. So the things we can't cancel out, the lead, the iodine, and the lead iodide, everything that's left becomes this reaction. And that is our net ionic equation. And like I said, that is what we are learning how to write today. This net ionic equation still has to obey the law of conservation of matter. As you can see, there's 1 lead, 2 iodines, 2 iodines. Okay, so all we've done in writing this net ionic equation is show the actual reaction that's happening in solution. We've canceled out all of those spectator ions that are just watching the reaction happen, and we've got the actual reaction that's leading to the formation of our solid, or to the formation of our gas, or to the formation of water. So here's another example. This one's really fun. The reaction on the left, or this solution on the left, this has silver nitrate. I know we haven't worked with silver nitrate yet. It's actually a pretty cool substance. They used to use silver nitrate to develop photographs. And so if you get this on your hand, like say we were working with it in lab, it will actually develop when you go into the sunlight. And so it will develop your skin by turning it black. It's kind of interesting, but don't go around trying it because silver is a toxic metal and you don't want it on your skin. But if it did happen on accident, your skin would turn black for a few days where it had silver nitrate on it. The solution on the left, that's sodium chromate, a nice cool yellow solution. And when you mix these together, we get a precipitate that forms. Okay, so this is a double displacement reaction. We have silver nitrate reacting with sodium chromate to form silver chromate and sodium nitrate. Okay, so again, the driving force for this reaction would be the formation of a solid. So this is called a precipitation reaction. So our molecular equation is going to show everything and their states of matter. So our silver nitrate is a solution, so it's aqueous, and so does our sodium chromate. But if we didn't already know that they were solutions by looking at the pictures, we would see, okay, this has nitrate, and that's always aqueous. And this has sodium, and that's always aqueous. So again, memorizing those couple things that are always aqueous will make this whole process a lot faster. So then we get to the other side and we see silver chromate. Okay, so silver chromate, that's not one you had to memorize. You would have to look that up on your solubility table. When you look up silver chromate, you would see an I. That means it's forming a solid, okay? And then sodium nitrate is aqueous because both sodium and nitrate are always aqueous ions. All right, once we write our molecular equation, now we can write our total ionic equation. Remember, our total ionic equation is going to split everything that's aqueous into its ions. So here that is. So our silver nitrate split into 2 silvers and 2 nitrates. Remember that 2 out front is going to distribute in to everything in that compound. So when this splits up, we get 2 silvers and 2 nitrates, and both are aqueous. And then we have sodium chromate. This 2 is telling us there are 2 sodiums. So that's why this 2 is out front here. So there are 2 sodiums and 1 chromate. And then our silver chromate solid stays together. Remember, the only thing you are going to split apart are aqueous ionic compounds. And then our sodium nitrate will split apart, and that 2 out front is going to distribute into the sodium and to the nitrate. So we get 2 sodiums and 2 nitrates. So that is our total ionic equation. As you can see, the sodium and the nitrate both show up in exactly the same way on both sides of this equation, right? So we can actually cancel those out. 2 sodiums, 2 sodiums, 2 nitrates, 2 nitrates. Those are our spectator ions. Okay, they are not participating in this reaction. To write the net ionic equation, we remove our spectator ions and then just bring down everything that's left. So what's left is we have 2 silver, our chromate, and that's making silver chromate. All right, let's go ahead and do some example problems. Here's one. This says lead 2 nitrate and potassium iodide are making lead 2 iodide and potassium nitrate. You'll notice I gave you words instead of the chemical formulas. This is so you continue to get practice on writing the formulas of ionic compounds. So let's go ahead and do that. So we have lead 2 nitrate. Remember, when we have a transition metal, they're always going to have a Roman numeral to tell you their charge. So here, lead 2 is telling us that is lead 2 plus. I think that's really handy, and I think it makes our lives a little bit easier. Nitrate is a polyatomic ion, that's NO3 minus. These charges are not equal and opposite, so we need to circle and switch. That 2 goes to the nitrate, and we get Pb NO3 2. Okay. Potassium iodide, we have potassium is K plus, iodine is I minus. Those are equal and opposite, so we're just getting Ki. The nice thing about doing the reactants is you already have the charges when you're going to go do the products. Like we already figured out lead 2 was Pb2 plus, and we already went and found iodine was I minus. These are not equal and opposite, so we need to circle and switch. That 2 is going to go to the iodine, and we get Pbi2. And then for potassium nitrate, we have K plus and NO3 minus. These are equal and opposite, so we get KNO3. So then we can write our reaction. So we see that lead nitrate is aqueous because it contains nitrate, and nitrate is always aqueous. Potassium iodide is aqueous because potassium is always aqueous. Lead iodide would be one that we would need to go look up. And so if you went and looked up lead iodide, you would see an I there for an insoluble solid. Therefore, that gets an S to say it forms a solid in solution. And then potassium nitrate is always aqueous because both potassium and nitrate are aqueous ions. All right, then just so you know, you would also need to go through and balance this chemical equation. I put the 2's in there already because I'm going to assume at this moment that you know how to balance equations. If that's not true and you're a little bit rusty on it, do make sure that you get some practice balancing equations. All right, so that is our molecular equation. That shows everything just like normal. Now, when we go to write our total ionic equation, we are going to split apart everything that's aqueous. So we're going to split apart the lead nitrate, the potassium iodide, and the potassium nitrate. The only thing that's going to stay together is our lead iodide. So here we are. So our Pb2 plus, and then we have 2 nitrates, 2 potassiums, 2 iodides. Our lead iodide stays together, and then we have 2 potassiums and 2 nitrates. So there we are. Now we would go through and cancel out all of our spectator ions. So remember, spectator ions are ions that show up on both sides of the equation in the exact same way. So our spectator ions here are going to be nitrate because it shows up as 2 nitrates on both sides, and potassium because it shows up as 2 potassiums on both sides. So our actual equation that's happening is lead is reacting with iodide to make lead iodide. So that is our net ionic equation. Let's try another one. Now you have a paragraph. So not only am I just giving you words, now I've given you a paragraph to sort through. Just so you know, this isn't normal. This is not how I will normally give you these types of problems. I may give you the word problems like you saw on the previous slide, but I really just like this example problem because this is a real world application. I would not probably give you one of these types of equations or reactions on a test because it's a little bit difficult to sort through. But we'll go through it as an example problem because, like I said, I really do like this. It's a real world application. So milk of magnesia is an over-the-counter laxative. So if you're ever taking milk of magnesia, be warned, maybe stay home for a couple hours after that. It's a mixture of magnesium hydroxide and water. Okay, so magnesium hydroxide is not soluble in water. If you were to go and look up magnesium hydroxide on your solubility chart, it will show an I, which means it's a solid at room temperature. However, as you can see here, they're pouring it out as a liquid. So the reason it's kind of like quote unquote a liquid is because it's a suspension. We don't learn about suspensions in this class, but essentially what a suspension is it's something that's insoluble, but if you shake it up really, really good, it will kind of stay in solution for a little while. It's not dissolved, right? That's why it's white, but it's kind of floating in solution, so it'll stay there for a little while. So that's what it says, a suspension. It's kind of just like hanging out in there, but it really is still a solid. It's not dissolved. When hydrochloric acid is added to milk of magnesia, the result is a clear, colorless solution. So if I took this cloudy white substance, and I poured in hydrochloric acid, then it would turn completely clear. Kind of cool. So this is actually a real-world example because milk of magnesia, in addition to being a laxative, is an antacid, which is kind of cool. So if you're not familiar with antacids, you take them when your stomach is feeling very, very acidic. Maybe it's giving you heartburn. And so you take an antacid to kind of calm down that stomach acid. Well, your stomach acid is actually hydrochloric acid, which is kind of weird, right? We work with hydrochloric acid in lab, but that's what is in your stomach too. It helps to digest food. So we will add milk of magnesia, which is a base. So we call it an antacid because, most people out kind of in society, if we said, okay, you have too much acid and so you need to add a base so that you have a neutralization reaction happening in your stomach, they would be like, whoa, chemicals, right? I'm not going to go for that. But if we tell them it's an antacid, then people tend to be more accepting of that. It's just something you take to get rid of some acid, right? And it's a base. So that's actually kind of interesting to me. So essentially what we're having reaction in our stomach is an acid-base neutralization reaction when you take this milk of magnesia. So let's go ahead and write our reaction for what's happening. So like I said, we're having hydrochloric acid added to magnesium hydroxide. When we have this, right, this is a base, and this is an acid, and we have acid plus base is always going to give a salt and water. So we have water, and then we needed to figure out our equation for our salt. So remember, the OH from our base and the H from our acid are what's making the water. So our salt is going to be made up of anything that's not those two. So our salt is going to be made up of magnesium and chlorine. So we have Mg2+ and Cl-. So when we circle and switch, that's where we're getting MgCl2. Okay, so this is an acid-base neutralization reaction. The driving force here is the formation of water. And so that's why it's saying that the result is clear, because we're making water. The other thing that we're making, magnesium chloride, if you look that up on your solubility chart, that's going to show you that magnesium chloride is aqueous. So our clear solution is an aqueous solution of magnesium chloride. You'll notice here that magnesium hydroxide is a solid, okay? That's what we're seeing up here. It was a suspension, so it's a solid. So this is going to change the way we write our total ionic equation and our net ionic equation because now both of our reactants aren't aqueous. So this will look a little bit different. Remember, you're only going to split apart aqueous ionic compounds. So here is our complete ionic equation. We are going to split up hydrochloric acid and magnesium chloride because those are our aqueous ionic compounds. We are not going to split up magnesium hydroxide because it's a solid. And we're not going to split up water because it's a pure liquid. So this will look a little different. So again, magnesium hydroxide stays the same. We're going to split up our hydrochloric acid. That 2 is going to distribute into the hydrogen and the chlorine. So we're getting 2 of each. And then we get our water. We have to leave water alone because it's not an aqueous ionic compound. And then we'll split up our magnesium chloride into magnesium and chlorine. You'll notice we're getting 2 chlorines because of that 2 there. So now we need to cancel out our spectator ions. In this particular example, we only have one spectator ion. That is our chlorine. everything else looks different on either side of the equation. So there it is. We have magnesium hydroxide, we have our two hydrogens are making water and releasing that magnesium ion. All right, I want you to do a few practice problems to get some work on this. So for each one of these, I want you to figure out whether or not a reaction occurs. Okay, we can always write a double displacement reaction, but if everything ends up aqueous in both the reactants and the products, then we're saying no reaction happens because everything is still aqueous. So essentially, we poured things together and a bunch of aqueous ions just like floated around. They didn't make a solid, they didn't make water, they didn't make a gas, they didn't do anything, they just kind of floated around. So that's a scenario, that's something that can happen. Everything can stay aqueous, and we'll say no reaction occurs. But if a reaction does occur for these, I want you to write the balanced molecular, total ionic, and net ionic equations, just like we've been doing, and I also want you to identify the spectator ions. So 3 problems here. Go ahead, pause here, and then come back when you're ready to go over it. Let's go ahead and go over this. So our first one is a reaction of aqueous sodium carbonate with aqueous barium nitrate. So the first thing we need to do is write out the normal molecular balanced chemical equation just like we've done for everything else. So we will need to figure out our ions first. So we have sodium is Na plus and carbonate is CO3 2 minus. These ions are not equal and opposite, so we need to circle and switch. So we'll get Na2 CO3, and that's aqueous. Even if the problem didn't say it was aqueous, we would know this is aqueous because sodium is an alkali metal and alkali metals are always aqueous. All right, our next one is barium nitrate. So we have barium is Ba2 plus, nitrate is NO3 minus. These are not equal and opposite, so we circle and switch. That 2 is going to the nitrate, and we get Ba NO3 2, and that's aqueous because it says so, but even if it didn't, we would know that that's aqueous because it has nitrate, and nitrate is always aqueous. All right, now we need to figure out the products. Okay, so again, we can think about this as foiling like we were doing before. So sodium will end up with the nitrate, and barium will end up with the carbonate. So sodium and nitrate, we have Na plus and NO3 minus. Those are equal and opposite, so we just kind of put them together. NaNO3, and that's aqueous. Now barium is going to go to the carbonate, and barium is Ba2 plus, and carbonate is CO3 2 minus. Those are also equal and opposite, so we get BaCO3. So this is one that we would need to go look up because it doesn't contain any ions that we needed to memorize. If you look up barium carbonate, you will see an I, which tells you it's insoluble and therefore makes a solid in solution. Okay, so now we're going to go through and write our total ionic equation. Our total ionic equation will split up all of the aqueous ionic compounds. Okay, so the first one we need to split up is sodium carbonate. Okay, that 2 is telling us there are 2 sodiums, so we will get 2 Na plus, and those are going to be aqueous. And we're also getting carbonate when that splits up, and also aqueous. Now we go on to, oh, my apologies. I just realized I didn't balance this equation. There we are. All right, sorry about that. Now we're going on to barium nitrate. So when we split that up, we'll get Ba2 plus, and we will get 2 nitrates. So 2 NO3 minus. And then on the product side, we're going to split up sodium nitrate, and that 2 is going to distribute in to both sodium and nitrate. So we'll get 2 Na plus aqueous and 2 nitrates, which are also aqueous. And then barium carbonate, we will not split up because barium carbonate is a solid. Okay, so that is our total ionic equation. Now we need to go through and cancel out our spectator ions. So you'll notice sodium shows up the same on both sides. So we'll cancel out our sodium ions. And nitrate shows up the same on both sides, so we'll cancel out our nitrate ions. So we're left with carbonate and barium are making barium carbonate. So that is going to be our net ionic equation. So there you go. I just copied down everything that we didn't cancel out from that total ionic equation, and that is going to be our net ionic equation for this problem. All right, let's try another one. So this one has ammonium chloride and sodium bromide. So again, first thing we need to do is write our balanced chemical equation. So ammonium is a polyatomic ion, that's NH4+, and then chloride is Cl-. These are equal and opposite, so we just get NH4Cl, and this is aqueous. So even if it didn't say it was aqueous, ammonium is one of those ions that you're supposed to memorize, and that's going to tell you this is aqueous. So then we have sodium bromide. So sodium is Na+, bromide is Br-. They are equal and opposite, so we just get NaBr, and that's aqueous. Okay, so then our products, when we FOIL, are going to be ammonium bromide. So we're getting NH4Br because those are equal and opposite, and that's going to be aqueous because anything that contains ammonium is always aqueous. And then the inside, we get sodium and chloride, so we get NaCl, those are equal and opposite as well, and anything with sodium is going to be aqueous because it's an alkali metal. All right, do you notice here that we have everything is aqueous? Everything is an aqueous ionic compound. So instead of going through this whole process, like if we were going to go through, and I'll just kind of do it for a point, if we were going to go through and split up all of our aqueous compounds, it would look like this. That should be Na. All right, so there we go. I went through and split up all of our aqueous compounds. Do you see that the ammoniums cancel out, the chlorides cancel out, the sodiums cancel out, and the bromides cancel out? So everything canceled out, right? This means that no reaction will occur, okay? Essentially, what this means is we mixed together aqueous solutions and the ions just all kind of floated around and looked at each other, but nothing actually reacted. So here we would say no reaction. This will happen if all of our reactants are aqueous and also all of our products are aqueous. All right, let's try this last one. This is hydrochloric acid reacting with sodium hydroxide. So hydrochloric acid, we have hydroic acid, which means it's a binary acid. So that means hydrogen is just bonded to chlorine, so HCl, okay? All right, sodium hydroxide. Sodium is a metal. We're very familiar with sodium, and hydroxide is a polyatomic ion. That's OH-. So we get NaOH because those are equal and opposite. So here, hopefully we'll recognize this is an acid-base reaction. We have H in the front, OH in the back. That's telling us acid-base. Anytime we have an acid and a base, they are always going to make water, which is a pure liquid, right? Be careful there. Water gets an L every single time. No AQ, always an L. So we have water and whatever's left over. So our leftover stuff is going to be made up of chlorine and sodium. Because remember, the H and the OH went to make water. So what we have left is NaCl. And that's going to be aqueous because anything containing sodium is always aqueous. All right, so that is our molecular equation. Now we're going to write our total ionic equation by splitting everything that's aqueous and ionic into ions. So hydrochloric acid will split into H+ and Cl-. Sodium hydroxide will split into Na+, and OH minus, water will stay together. Never, ever, 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 ever split up water. Remember, water is a pure liquid, so we won't split that up. We only split up things that are aqueous because those are soluble ionic compounds that dissociate into ions. So then we can split up our sodium chloride into sodium and chlorine. All right, so now we need to go through and cancel out our spectator ions. So we can see we have sodiums on both sides and chlorides on both sides. So our net ionic equation is actually showing the formation of water. So we have H plus OH minus is giving us water. Anytime you have an acid-base reaction, this will always be your net ionic equation. Kind of cool. Alrighty, go ahead and practice these skills. I want you to complete problems number 8 through 11 on the Chapter 10 lecture worksheet. And this is actually the end of Chapter 10. Okay, we covered a lot of ground today. We learned how to write the molecular equation, which we said was just the balanced chemical equation that we were writing for these double displacement reactions. We also learned how to write our total ionic equation by splitting all of our soluble ionic compounds into their ions, because those are what they would dissociate into when we put them in solution. We were then able to cancel out our spectator ions, those ions that are just watching the reaction happen. And when we cancel out those spectator ions, we're left with the net ionic equation. That net ionic equation is showing the actual reaction that occurs in solution. Okay, so lots of ground that we covered today. This lecture allows you to now go and complete the net ionic equations lab. Okay, that is worth points. It's a worksheet, it's worth points, just like any other lab, and it's designed to help you practice writing these net ionic equations. So I would recommend do these lecture worksheet problems first to make sure you're super solid on how to do these 3 different types of reactions. Once you're feeling really comfortable with that, then go and tackle the net ionic equations lab. As always, if you have any questions, please send them my way. I'm more than happy to help you out. I know these net ionic equations can be a little bit tricky when you're trying to get familiar with them, so please feel free to ask if you have any questions at all. Otherwise, keep working hard, and I'll talk to you guys next time.